All right, in this video, we're going to be talking about irrational numbers. And this is a really significant moment in 8th grade because you're actually being introduced to an entirely new type of number. And it's a whole different concept from anything that you've had explained to you before. And so we really need to look at like why, what does this mean? Even though you've done new things with decimals and fractions and other types of rational numbers, you haven't really had a new type of number introduced to you in a long time. Before we even explain what the number is, I want to give you a little bit of the history because this is really significant. When we first see irrational numbers come up in history is quite a while back, about 2,500 years ago. This is during the era of the Greeks. Sort of the beginning of it, I believe, and the Greeks were one of the most advanced civilizations the world had ever seen. And one of the things that they were really big on was math. They sort of pioneered a lot of what we still use today. And at the time, math was just geometry. It was observing the world around them. It was about shapes and angles and people saying, wow, okay, so, I noticed that the shape of the trunk of this tree is the same shape, as the stem of a flower, and is the same shape as, these other things that are circular, maybe even kind of what stars maybe look like at the time. And the moon was a circle. And wow, why are all these circles in nature and in squares? There's these angles and corners, and there's these different shapes, and that's what math was. And comparing those and measuring them, the idea of algebra, where we have x and these big kind of calculus-like things, don't come around for another 1,000 years. So the Greeks were religious and believed that gods were perfect. And at the time, there was sort of the Greek mythology of Greek gods, but there were also other little religious sects, but all of them believed that God was perfect. That's sort of the idea of God, or maybe they found their belief in God through the pursuit of perfection. And they looked at the world around them, and they tried to find evidence of God by finding evidence of things that they thought were perfect. And they said, wow, okay, all of the things that we're finding that are perfect, that are always predictable, that are never wrong, that are reliable, that are always definable, are all based on math. The notion that gods lived in the sky came from their belief that the universe was perfect, that it was fixed, that it was always reliable, everything was there and would always be there and had always been there. And so they believed that must be where the gods live, is amongst perfection. And they also believed that music was math translated for us. And notes and sounds are all based on math, and therefore music is a divine. This is really where we see music being considered a part of religion. So now, back 2,500 years ago, there was this pretty famous guy named Pythagoras, and he was a math dude, a pretty famous one, still is. And he was a big believer in math being the language of gods, because he believed math was perfect, and therefore that must be how that must be their blueprint, right? The reason that all of these things in nature are built on math is because it's their God's perception of how things should be, and therefore it's perfect, and therefore math must be perfect. And one day a friend of Pythagoras's, his name was Hippasus, said, I've discovered something amazing. I didn't finish my quotation, sorry. The two friends went on a boat. We're better to discuss math than on a boat. And Hippasus told Pythagoras his story. Now, before I tell you what Hippasus told Pythagoras, we need to understand a little bit about what Pythagoras was kind of famous for. He had discovered this pretty simple but amazing theorem that said a squared plus b squared is c squared, and we now call that the Pythagorean theorem. So here's the notion. If you create a right triangle, which means a 90-degree angle there, kind of like a corner, and I've created one here, and I've put rulers in so you can see. This is 4 inches, and this is 3 inches. So if we take this triangle that's got one side that's a length of 4 and one side that's a length of 3, if we square those sides, right? So here's the side that was 4 inches, right? So this side's 4 inches, so that side's 4 inches and 4 inches. We've just made a square using one of the legs of the triangles. And I've made another one over here. This was 3 inches. And then I've now made a square out of what's called the hypotenuse, or this kind of slanted side that's across from the right angle. And I'm saying, if I know this side and this side, I can figure this side out. Because if the area of this square, which since this was 4, the area of a square is 4 times 4, so we wind up with 16 squares in here, right? 4 squared, a squared. And here this was 3, so that when we square 3 or multiply it by itself, we get 9. And we said, hey, you know what? If I take each one of these squares and fill it into this block, right? And I've rotated them here. It's going to be the exact number of squares from here and here. So if you take this side and square it and this side square it, then it's going to be the number of squares in the hypotenuse when you square the hypotenuse, right? We made a square off the hypotenuse, and this fits in here. So let's see, there were 16 here and 9 here. So how many squares are there total? That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20, 25. So this square is 25. And now we say, hey, okay, well, if this square is 25, then I can take the root of that, right? What number times itself equals 25, and that'll be the length of any one of the sides, including this hypotenuse. And we say, well, that's 5, right? 5 times 5 is 25. And sure enough, we can take our ruler here and look, and yep, it looks like it's exactly 5 inches. So this was Pythagoras' big discovery. So Pythagoras was pretty proud of this. So back to our boat trip. Hippasus said, check out this, mate. If you have a triangle where each side, let's say, has a length of 1, then the hypotenuse must be the square root of 2, right? 1 squared is 1 plus 1 squared, right? Those are the 2 legs. That equals 2. So the square built on the hypotenuse is 2. Therefore, the side must be the square root of 2. And he said, now check this out. This number is not like anything we've seen before. It can't be represented as a fraction. It never ends. If you divide it over and over and over, the decimal will continue on forever. All right, so Pythagoras said, that's crazy. That would mean that math's not always perfect because the number would never resolve. It never actually comes to a conclusion. It goes on and kind of rambles forever. It can't be defined, and therefore it's not perfect. And he tried to prove Hippasus wrong. The square root of 2 means some number times itself equals 2. Well, let's see if we can figure that out, okay? So he said, well, okay, I know that it's got to be a number between 1 and 2. Let's try 1.5. 1.5 times 1, oops, it's not typing for me. 1.5 times 1.5, what does that equal? Okay, that's bigger than 2. So each side must be less than 1.5. Let's try 1.4. 1.4 times 1.4. He said, okay, that's close, right? We're already close. Of course this will work. So 1.4 was right below it. So let's try 1.42 times 1.42. Oh, nope, that's too big, right? So we got to go back to the drawing board. What about 1.41 times 1.41? No? Okay, well, we got to keep going. 1.414 times 1.414. What does that do? Oh, we're so close. And he kept going, but it just kept more and more nines. It kept getting closer and closer, but he could never find 2 numbers that multiplied together to equal 2. Well, NASA went a little bit further. Oh, it took away my browser. Okay, so I think I still have this window open. Hold on, let me... no, I don't, but I can find it very quickly. So we can go to NASA square root of 2, right? Here we go. NASA has written the square root of 2 out to the first million digits, right? 1.414. We got that far. Well, they kept going and kept going and kept going. I don't even know if you can tell. Look where my scroll is. I mean, look at how many numbers. This is just going on and on. That's the first million digits, and even that doesn't equal 2. Well, this made Pythagoras mad. So he killed Hippasus. He threw him off the boat. That's the end of that story. An irrational number is a number that never ends. And that means that its decimal representation goes on forever and ever. And the concept of something that never ends, that goes on forever and ever, is called infinity. And this is this amazing concept in math. Any fraction will be rational because it will repeat eventually. 2 goes into 1. Oh, well, it doesn't. Okay, so let's try moving over to our tens place, right? We'll add a 0. 2 goes into 10 how many times? Well, 5 times. And there's no remainder. How many times will 2 go into 0? How many times will 2 go into 0? How many times will 2 go into 0, right? And it's just going to repeat zeros forever. So it repeats eventually. How many times will 3 go into 2? Well, it won't go into 2. Let's go over to our tens place, right? So how many times will it go into 20? Well, it goes into 20 6 times. 18, a remainder of 2. How many times will it go into 20? 6 times, remainder of 2. How many times will it go into 20? And you can see this pattern. Once again, we're just carrying down more zeros as we move across the place value. You can see that this is going to repeat 6s forever. On and on and on forever. So this is a rational number, 2 over 3. However, a number that never repeats. Imagine if you had a piece of paper and you divide it in half, and then you cut it in half again, and again, and again, and again, and again, and again. You would never reach 0, right? There would always be a new segment to cut in half. That is infinity. We made a triangle with legs of length 1. The hypotenuse would be between 1 and 2. So then if we divide that ruler into tenths, it'd be between 4 and 5. And then if we divide it into hundredths, it'd be between 1 and 2 again, and so on and so on. No matter how many times you zoom in on that ruler, the length of that hypotenuse will always be between 2 marks. It'll never be right at a mark because it goes on forever. Now, there are really 2 ways that you're going to see an irrational number written. An irrational number are roots of numbers that are not perfect. So take, for example, right, the square root of 2. There's no number that multiplied by itself equals 2 that's rational, right? It's that 1.4 never-ending number. However, the square root of 9, right, that's not irrational because that just equals 3. It repeats, right? 3.000, blah, 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 but we don't have to write all that. The square root of, 100 is obviously just 10. But the square root of, say, 95, well, there is no number times itself that equals 95. So this is irrational. And if we wanted to represent that in decimal form, it would be a decimal that never repeats. So let's look at some examples. We've got 7, rational or irrational, right? Well, it's just 7.0 repeating, so that's rational. 1/3 is, well, it's a fraction, so it has to be rational, right? And you could put it in decimal and see that it repeats, 0.3 repeating. The square root of 25, that's 5, which could be seen as 5.000, it repeats. 0.6 repeating, well, it repeats, that's rational. However, the square root of 5, there's no number times itself that equals 5, so this must be irrational. Now, this is an important one to notice. This is a pattern, but it never repeats, right? 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7. And these dots, we assume this pattern continues. 1, 8, 1, 9, 1, 1, 0, 1, 1, 1, 1, 1, 2. Even though there's a pattern, there's no segment, right, that repeats. It doesn't repeat 1 forever. It doesn't repeat 1, 2 forever. It doesn't repeat 1, 2, 1 forever. It doesn't repeat 1, 2, 1, 3 forever. So there's never actually anything repeating. So this is irrational. We also need to be able to roughly approximate these numbers on the number line. So we say, okay, the square root of 5. Well, okay, the square root of 5. Here's what I do know. I know that the square root of 4 is 2. So this is bigger than the number 2. And I know that the square root of 4 equals 2. And I know that the square root of 9 equals 3. So since 5 is smaller than 9, that means this number must exist somewhere between 2 and 3. The square root of 35, well, the square root of 25 is 5, and the square root of 36 is 6. This is between 5 and 6. The square root of 49 is just 7, so it's right at 7. The square root of 8 is 6. The square root of 64 is 8, and the square root of 81 is 9. So this is somewhere between 8 and 9. That's all we're talking about. So anyways, that's sort of our little introduction to irrational numbers. A little bit strange, but I hope it helps. Thank you.